Good afternoon. Myself S.R.Barbade, Assistant Professor, Electronics and Communication Engineering, Walchand Institute of Technology, Solapur. Today we will discuss image basics and its representation. Learning outcome of the session. At the end of this session, students will learn basic terminology and representation used in image processing. Contents. In the slides we follow, we are considering what is involved in capturing a digital image of a real world scene. In that, we are going to discuss image representation, image sensing, sampling, quantization, and image resolution. First, we will see what is image representation. Actually, the first step in image processing is image acquisition, but we need to know how the image is represented in a computer's memory. That's why before we discuss image acquisition, recall that a digital image is composed of m rows and n columns of pixels. The m rows starting from 0 to m minus 1, and there are n columns starting from 0 to n minus 1. These are the pixels at each intersection of the rows and columns. So image we consider as a matrix of pixels, and the pixel values are most often gray levels in the range 0 to 255 for black and white image, and for color images a single pixel is a combination of 3 colors. Say for example, in RGB color model, red, green and blue forms a single pixel. Thus we can say that images can easily be represented as matrices in a computer's memory. Now we will go to the image sensing, also called as image acquisition. Image is acquired, or to acquire the image we require 3 main components. One is an object. This one is the object to be sensed, or we can say scene element, and we require a sensing system or imaging system or camera, we can say. This is what the camera to be used for sensing an object, and in addition to this we require the illumination also. So this object is illuminated and these rays are reflected on the sensing elements present in the imaging system, and the image matrix we can observe like this. So this is what an image plane which is inside this imaging system. So this is the external object and this is the object inside the imaging system, that is on the sensors. But this object is in the form of analog signals. To process the image in digital form, we require to convert the image into digital That's why we need sampling quantization that we will see in the next slide. So once the image is acquired in the imaging system, which one is an analog one like this? This is what the image acquired by the imaging system, which is analog in nature. But we need this to be converted into digital. That's why we require image sampling and quantization. A digital sensor can only measure a limited number of samples at a discrete set of energy levels. So the sensor, if it is digital one, then there is no need of converting into digital. But if it is a analog sensor, then we need to convert into digital by using sampling technique. So after sampling, we see that this is what the result of sampling the image from point A to B from left to right. As we see here, as we go from point A to B along this line, we observe that there is a bright pixels in this region. That's why the magnitude of the pixels is high here. It is shown here. Abruptly at this edge, the brightness of the pixel is dark. That means from white to black transition is there. So that's why this transition from high to low is there. After that, the brightness is increasing. As you see here, this is darkest point, and as we go along this line towards right, the darkness is decreasing. That means whiteness is increasing. You just look at here. This is a profile of this intensity along the line AB. At the center, we look at there is a maximum intensity, and again from this point, again, it is decreasing up to this point. That's why this is also decreasing, and from this edge to point B, there are white pixels. That's why this is again going to the high magnitude. So this is what the result of sampling an image on the line AB. This is sampled at these discrete levels, and now we should convert this into digital form by using the 3-bit quantizer, which has 8 different gray levels. This is a darkest one and this is a bright one. Sample is converted into digital by using this gray levels. If you look at to the right side, these are the values. For example, this is the first sample whose value is this one. So these are the sampling points. The value of this signal is taken at this point only. Second is at this point. Third is at this point. There is no value in between. That's why there is a space between these two samples. So this is actually a sampled image, we can say. Lastly, we see the resolution of an image. Image resolution is of two types: the spatial resolution and intensity level resolution. The spatial resolution of an image is determined by how sampling was carried out. If the sampling is carried out very frequently, means the spatial resolution will be more. and the image quality will be good. Intensity levels used to represent the image pixel actually. So image pixel is represented by how many bits? If it is represented by 8 bits, then we can have 256 gray levels. If it is represented by using 10 bits, we can have 1024 intensity levels. So how many bits you are using to represent the pixel, the number of bits used to represent the pixel, more will be the intensity level resolution and more will be the clarity of the image. For think and write. Question is resolution increases when intensity levels are increased? You pause the video for some time and write down your answer. Answer will be yes. In summary, what we have looked at is image representation, image sensing, or it is called acquisition, then sampling, quantization, and resolution. References for this, I referred Digital Image Processing by Rafael C. Gonzalez and Richard E. Woods from Tata McGraw-Hill Education Publisher. Thank you.